Hi, my name is Kenan Sheikh from Lund University, and I'll be presenting to you our paper, LassoBench, High-Dimensional Hyperparameter Optimization Benchmark Suite for Lasso. This is joint work with Alexander Granford, Joseph Salmon, and Luigi Nardi. Let's start with the assumption that we want to predict a health condition of a patient based on a dataset with multiple different features from different patients, as illustrated on this figure, where features are like gender, nationality, age, and similar. The simplest approach would be to use a linear model, as done here. But why a linear model? Linear models are typically favorable due to their interpretability and good predictive performance, typically found in practice. Then a linear model can be solved with the method of least squares, that is, to find optimal regression coefficients, betas, minimizing the loss function. However, using the method of least squares becomes impractical due to multiple factors, such as having collinearity within features or having undetermined system, outliers, and similar. But data such as our for example, or detecting signals in brain imaging may include thousands of features, of which only a few are important for prediction. This important prior should be incorporated in the loss function to improve prediction and address dimensional limitations. So we add the penalty term as seen here that help us to control the size of regression coefficients. The acronym Lasso stands for least absolute shrinkage and selecting operator, as it is based on the L1 more. The main focus of this talk is this hyperparameter lambda, on which we focus next. The hyperparameter lambda is noted as a shrinking parameter that controls the size of regression coefficients and amount of regularization. The least square estimation is derived for lambda going to 0. For lambda going to infinity, all regression coefficients become 0. Thus, finding the optimal lambda is an interesting optimization problem. In standard Lasso model, we assume to have a single uniform lambda for all features that reduce the marginality of a problem to only 1D. However, by doing so, we introduce certain limitations, such as Lasso solution being biased, or often, let's say, with cross-validation with too many false positives, which in applications such as medicine can be dangerous. Therefore, it's crucial to stay in high-dimensional setting and find optimal lambda for each beta. In general, we talk about nested B-level high-dimensional optimization problem, where the regression coefficient beta are found with coordinate descent for specific lambdas. The auto-optimization part is used to select the optimal lambdas based on some criteria, such as cross-validation. For 1D, this is simply solved with grid search. In general, the objective is here defined in axiom aligned subspace, as each lambda that corresponds to 0 beta can be seen as dummy variable. The latest progress in high-dimensional HBO, such as Rainbow, Hesbo, Alevo, Turbo, CMES, and others, opens up the possibility to use one hyperparameter per feature. In particular, we can recognize three popular types of approaches to deal with high-dimensional problems, as illustrated here. In first place, we talk about embedding-based BO methods, where we project the original high-dimensional search space to low subspace that is practical for optimization. The main assumption is that the objective function contains a low-dimensional subspace called the effective dimensionality that mainly describe the variability of the target. In trust region-based methods, exploration and exploitation are done locally in high-dimensional space within the trust region. And lastly, evolutionary strategy, population-based and naturally inspired algorithms mostly focus on sampling techniques and do not include any modeling of a black box model. In addition to solving this important open question in the Lasso community, we have noticed that the literature about high-dimensional HBO lacks practical high-dimensional benchmarks. Therefore, we introduced the open source package LassoBench based on the weighted Lasso regression that provides a platform for newly proposed high-dimensional HBO methods to be easily tested on different synthetic and real-world problems. It's a new highly dimensional and multi-fidelity HBO benchmark suite. LassoBench exposes many features that we discuss next, which enable the use of many flavors of BO algorithms to improve and extend it to highly dimensional setting, and easily used in only 4 lines of code as demonstrated here. The user can decide between synthetic and real-world benchmarks with different ambient and effective dimensions. In total, we have 13 benchmarks, as each synthetic benchmark comes with a noisy and noise-free version. effective dimensions are and active hyperparameters are well defined and provided. While real-world benchmarks are based on real datasets, commonly found in the Lasso community, synthetic benchmarks are based on the predefined regression coefficients on top of which we create synthetic dataset. Higher dimensional benchmarks in Lasso comes also with the multi-fidelities. To best to our knowledge, the literature does not cover high dimensional and multi-fidelity benchmarks. We see LassoBench setting the stage for future research on this topic. The main load comes from the inner optimization loop that is current descent that approximates the regression coefficients. Being an iterative solver, the coordinate descent budget can be used to define different fidelities. That is, changing the tolerance level parameter leads to faster and less accurate solutions. On this figure, we can see a strong correlation between different synthetic fidelities that can be utilized in multi-fidelity algorithms. We cover both types of multi-fidelity scenarios found in the literature, discrete and continuous fidelity. On this slide, we show how the user can easily select the benchmark, for example, RSV1, the type of the multi-fidelity scenario discrete, and evaluate the objective function that is validation loss. In our study, we compared the performance of popular high-dimensional HBO algorithms, such as Alebo, Hesbo, Turbo, CMES, and Hyperparameter, with respect to the Lasso baselines, and randomly search for different synthetic and real-world benchmarks. For Sparse HO, which is a newly proposed Lasso baseline, after 20 iterations, which is typically corresponds to convergence, the procedure is initialized with the new initial configuration until the budget is exhausted. Noted here as the new approach, multi-start Sparse HO. The first example is synthetic high, which has 300 parameters and the effective dimensionality of 50. While high-dimensional HBO methods such as Turbo and CMES easily exceed the Lasso-based 1D methods with grid search, that is LassoCV and adaptive LassoCV, the performance are very close with respect to the multi-star Sparse HO. For more elevation, Turbo and CMES can easily find better estimations than Sparse HO. Turbo generates slightly better results than CMES. Still, for higher dimensions such as synthetic hard with 1000 dimensions, the performance of Turbo drops significantly. CMES remarkably keeps a good performance and eventually being the best method for the noisy version. In the noiseless, Sparse HO still took the lead slightly. In general, the performance of Lasso-based 1D methods keep improving with higher dimensions. In RSV1, the real-world benchmark with the highest dimensionality over 90,000, the Lasso-based 1D method LassoCV provides the best solution, followed by adaptive LassoCV. Using Turbo in this example becomes impractical due to memory budget, as we need to train a stronger model in over 90,000 dimensional space. In leukemia, CMES shows the best performance, leaving all other methods significantly behind. So in the absence of practical high-dimensional benchmarks, the open source package LassoBench based on the latest Lasso provides a platform for newly proposed HBO, high-dimensional HBO methods to be easily tested on different synthetic and real-world problems. Our results showed that the high-dimensional Bayesian optimization methods and evolutionary strategy can indeed provide better estimations than the standard Lasso baselines. It opens up a new way of thinking about HBO for high-dimensional Lasso problem, getting the Lasso community one step closer to democratizing weighted Lasso models. Still, scaling to higher dimensions, typically encountered in the Lasso community for real-world application, represents an open research question. Thank you.